In our last lesson, we derived Poisson's and Laplace's equations from Gauss's law. Poisson's equation relates the Laplacian of V to the charge density, while Laplace's equation applies in charge-free regions. We also introduced the four-step solution procedure: integrate the equation, apply boundary conditions, find E, then find other quantities. Today, we apply these tools to derive general expressions for resistance and capacitance. Let's start with resistance. Consider two conductors maintained at a potential difference V0. To find the resistance between them, we follow these steps. First, choose a suitable coordinate system and solve Laplace's equation to find V. Second, find E from E equals negative gradient of V. Third, find the current density, J equals sigma E, and integrate over the conductor surface to get the total current. I equals the integral of sigma E dot ds. Finally, the resistance is R equals V over I. This gives the general formula. R equals the line integral of E dot dl divided by sigma times the surface integral of E dot ds. Notice that we solve for the field first, then derive resistance from the field solution. We don't need to know the charge distribution. Now let's find capacitance. A capacitor consists of two conductors separated by a dielectric. When voltage V is applied, charge Q accumulates on the plates, and C equals Q over V. The general formula is C equals epsilon times the closed surface integral of E dot ds divided by the line integral of E dot dl. Let's apply this to three common geometries. For parallel plates with area S and separation d, the electric field is uniform. E equals V over d. Integrating gives C equals epsilon S over d. This is the most fundamental capacitor formula. For a coaxial cable with inner radius A and outer radius B, the field varies as 1 over rho. The capacitance per unit length is C equals 2 pi epsilon L divided by the natural logarithm of B over A. For concentric spheres with radii A and B, the field varies as 1 over r squared. The result is C equals 4 pi epsilon divided by the quantity 1 over A minus 1 over B. There is an elegant relationship between R and C for the same geometry. R times C equals epsilon over sigma. If you know the capacitance, you can immediately find the resistance and vice versa. Let's work a numerical example. A parallel plate capacitor has square plates of side length 10 centimeters, separated by 2 millimeters. The dielectric has relative permittivity epsilon R equals 3. A voltage of 200 volts is applied. Find the capacitance, charge, and stored energy. Step 1. Convert units. The plate area is S equals 10 centimeters times 10 centimeters equals 100 square centimeters. Converting to SI, S equals 100 times 10 to the negative 4, which is 0.01 square meters. The separation is D equals 2 millimeters equals 2 times 10 to the negative 3 meters. Step 2. Find the permittivity. Epsilon equals epsilon r times epsilon 0 equals 3 times 8.854 times 10 to the negative 12. That gives epsilon equals 26.562 times 10 to the negative 12 farads per meter. Step 3. Apply C equals epsilon s over d. Substituting, C equals 26.562 times 10 to the negative 12 times 0.01 divided by 2 times 10 to the negative 3. This gives C equals 132.81 times 10 to the negative 12, which is 132.81 picofarads. Step 4. The charge is Q equals CV. Q equals 132.81 times 10 to the negative 12 times 200. That gives Q equals 26.56 nanocoulombs. Step 5. The stored energy is W equals 1/2 CV squared. W equals 1/2 times 132.81 times 10 to the negative 12 times 200 squared. 200 squared is 40,000. So W equals 1/2 times 132.81 times 10 to the negative 12 times 40,000. That gives W equals 2.656 microjoules. Let's summarize. The general resistance formula uses the field solution. R equals the integral of E dot dl over sigma times the integral of E dot ds. For capacitance, the three key formulas are parallel plate, C equals epsilon S over D, coaxial, C equals 2 pi epsilon L over ln B over A, and spherical, C equals 4 pi epsilon over 1 over A minus 1 over B. The elegant result, RC equals epsilon over sigma, connects resistance and capacitance for any geometry. In our next lesson, we'll explore the method of images.